Lesson members, and today we are going to look at circular motion, Newton's laws, and linear momentum. In the previous video, you must have seen linear motion, where we are looking at a body that is moving in a straight line. Now we want to see when a body is not moving in a straight line. My name is Teacher Ahebo William. Let's start by looking at circular motion. When we say circular, like you already hear, it means circular comes from circle, correct? So that means we are looking at a body which is moving in a circle, or a body whose motion is more of a circle. And as we always know, that a circle is in some way having a point which acts as a center. So a body which is moving in a circle is more of it is almost rotating a certain point. That's why you call it motion. Examples of circular motion, it is like when you have, let's say, a stone or a pendulum bob, you tie it on a thread and you start swinging it in air. That is an example of a circular motion, meaning the pendulum bob will be describing a circle as you're holding it, rotating it, or spinning it. It may be vertically or horizontally. That is a circle. An example is like planetary motion. You must have looked at the solar system and how planets move around the sun. So they describe a circular motion. It may be a car or a bicycle moving around a corner. That is still circular motion. It may be children playing on the swings, these swings which rotate, or circus. That is all circular motion. Let's look at this illustration and we see. Okay, so now let's look at these two bodies. For example, I've used this sample as our body which is describing a circular motion. We have here our planet Earth. We have the moon that is rotating the Earth. So meaning the moon is describing a circular motion. For example, you can see it is moving. It is moving in a circular motion. Now, one thing you notice is that its direction keeps on changing. At this point, it appears like it is going here. The other point, it appears like it is going there. So the direction keeps on changing. And also, its velocity keeps on changing the direction. You realize at this point, it is heading that side. At the other point, it is heading the other side. So the velocity keeps also changing. There is another thing that I want you to observe. When a body is moving in a circular path, it appears like something is holding it, like the way you'd be swinging a pendulum bob. Now, for this case, it is due to gravity force. Now, the blue lines are indicating for you the gravity. Now, this gravity is holding the moon in that circle because it appears like it wants to come towards the center, but also as if there is another force pushing it away not to come to the center. As a result, it ends up keeping in this circle. Now, this force which is pulling it towards the center is what we call the centripetal force, and the force which is pulling it out, that is what we call the centrifugal force. So now you're already observing the forces. Though the mass here, we cannot show it, the weight of this, we cannot show it directly, but these are some of the forces that are acting on our body, which is describing a circular motion. We see there is a centripetal force. It will always pull it towards the center. There is also a centrifugal force that will always try to push it out of the center. Now, these two forces are always equal. That's why you see this line is almost equal to that line. So they are always equal. That's why a body will keep in that circle. Otherwise, if this one becomes bigger than that, it means it will push the body and the body will not be in a circle. And if this becomes bigger than this, it means the force pulling it towards the center will be now overpowering and the body will end up coming to the center. So that's one scenario, or that what I wanted to show you, how a body that is moving in a circular path, the forces that are around it. Now we see that for a body that was moving in a circular path, one, its direction and velocity were constantly changing, and two, we said that it is having what we call the centripetal acceleration. That acceleration it is carrying is centripetal because it is moving in a circle, and it also has a force which pulls it towards the center, which we call the centripetal force, and the force that pulls it outwards from the center is what we call the centrifugal force. Now, in general, the forces that are acting on the body one of them, if it is a pendulum, you have tension. The other one which holds it towards the center. If you have a string, there's tension in that string. You have centripetal force that is pulling it towards the center. You have centrifugal force, then the weight of the body itself. So in a summary, we have said that a body which is moving in a circular motion, or a body which describes it moves in a circle, is what we call that kind of motion. We shall be calling it a circular motion. Then it is always changing the direction, and the velocity will always keep on changing because it is in a circle. The force, it will have a force that pulls it towards the center, known as a centripetal. It will be having a centripetal acceleration, and then it will be having that force which is known as centripetal force, whereas the force which pushes it outwards is what we know as centrifugal force. Then there will also be its own weight. So those are the forces that act on a body that is moving or describing a circular path. So the forces are as shown here in the diagram. So that gives us a recap of circular motion, or for a body that is moving in circular motion, what exactly happens, what are the forces around it. Now let's dive into linear momentum. Now momentum, I don't know how you understand it, but basically momentum, when you're talking about momentum, you realize you normally talk about momentum in terms of speed. Something that is carrying momentum, it is in terms of speed, and that is because momentum is a product of mass and its velocity. It means for me to get linear momentum of a body, I'll have to get mass. I multiply mass of that body, I multiply it with its velocity, and so that is what we call linear momentum for a body that is moving in a straight line. Its momentum will be the mass times its velocity. It means its unit will be the kilogram, which is for mass, then meter per second, which is for velocity. So kilogram times meter per second gives you kilogram meter per second. So that is the SI unit of momentum. Well, it shares a unit with the impulse. We shall look at impulse in another video. Now we talked about velocity earlier on, and we saw that velocity changes. So it means if velocity changes, even momentum of a body will do what? Will change. Now it means if I want to know the change in momentum of a body, I will have to get its final momentum. I subtract off its initial momentum. This is crucial. We are going to use it somewhere. Now if final momentum, it means now I need to get the mass of the body times the final velocity it is carrying. I take off the mass of the body times the initial velocity it had, which will be summarized as mv minus mu. Now linear momentum has a principle. There is that momentum must always be conserved. Now that principle is called the principle of conservation of momentum. What does it say? It states that when two or more bodies collide, the total momentum remains constant, provided no external force is acting. What do they mean? That if two bodies are coming together, one body is carrying its momentum, another body is also carrying its momentum, the total momentum they have before they collide will be the same total momentum they will have after they collide. Basically, that's it. That when two bodies collide, the total momentum before collision is equal to total momentum after collision. If we want to understand it better, let me give you here a scenario for context purposes. That if we have a body whose mass is m1, and it is moving with the velocity u1, because it is body 1, it is moving with velocity 1. Then it collides with another body of mass m2, which is moving with velocity u2. After they collide, you cannot tell me that they will continue moving with these same speeds. No, they will be changing speeds. Now, after they collide, body 1 moves with this velocity, final velocity v1, and body 2 moves with final velocity v2. It means that their total momentum before they collided, meaning momentum for body 1 was m1 times u1, which is m1 u1. If we add it with the total momentum of body 2, which was m2 u2, that answer should be the same answer you will get when I deal with their final momentum, which is m1 v1 plus m2 v2. This is what we are talking about in this case. So this is for the principle of conservation of momentum. When we talk about collisions, you already know colliding and how things collide. But we basically have two categories of collisions. That is elastic collisions. Under elastic collision, this is where bodies will collide, and after they collide, they separate. Each one goes its own path. Whereas we have also an inelastic. Inelastic collision is where the bodies will collide, and then after colliding, they will stick together after they have collided. So let's look at this scenario here to understand more about elastic and inelastic collisions, then the principle of conservation of momentum. Let's have a quick look at our two bodies. We examine and see what collisions are. We've already talked about the two types of collisions, that is elastic and inelastic. To remind you, we said elastic bodies will separate after they collide, whereas inelastic they will stay together after they collide. Now let's examine, let's look at it in real life. We have our two bodies, one being a red box, another one being a blue box. The red box is having a mass of 5 kilograms and a velocity of 8 meters per second. The blue box is having a mass of 4 kilograms and a velocity of also 8 meters per second, but it is moving in the negative direction. So that's why it is having a negative sign. So it will be having, because velocity is a vector, so the direction matters. That's why it is having a negative. Now, when we run, the two bodies, they will come together, they collide, and they separate after collision. That symbolizes for us what we call elastic collision. Let's now look at what it might look like for inelastic, meaning they will stay together after collision. Now, the two bodies are coming together, they are sticking together after collision. You can see red is now pushing blue. Why? Remember, before they collided, red had a total momentum. Remember, momentum is mass times velocity, which is 5 times 8, which is a momentum of 40 kilogram meter per second. Whereas blue had a total momentum of 4 times negative 8, which is negative 32. Okay, even if we ignore the negative, because negative is basically showing us the direction, but still you see 32 is less than 40, meaning even when they collide, red is more powerful than blue, meaning red will push blue. That's why we see that after they have collided, we see red is pushing what? Is pushing blue. Okay, that has shown for us what we call elastic and inelastic, but this was for the case where the bodies were moving in opposite directions. Let's examine and see when these bodies are moving in the same direction. We see what it looks like. Let me just make blue to have a velocity of 3 and the mass remains the same. I leave red to have this velocity with the same mass, but they are all moving. Now when I make this positive, it means I'm now forcing it to be moving in that direction also, a direction of positive. So when I test them, I see the two bodies are coming together. The red is chasing blue. When it reaches, it collides and they stay together. So that is indicating for us what inelastic collision looks like when the bodies are moving in the same direction. Whereas we can as well test to see elastic collision where they will separate. They were moving in the same direction, then they end up separating after they collide. Let's test it and see. The two bodies are still running. Red is chasing blue. It is reaching blue. It knocks it and they separate. Everyone is moving with a different velocity. So that is for elastic collision. You realize I'm being so slow when I'm talking about the type of collision, because I know you can easily confuse. So that's how the two collisions look like. Now allow me to quickly talk about the law of conservation. You must have seen something. If you rewind this video, I will just talk about this, but you can go back and study the figures I was talking about. Now, the law of conservation of momentum, we said that the momentum before collision is always equal to the momentum, total momentum after collision. Now we see these two bodies before they collide. The momentum for red is 5 times 8, which is 40. That is what we call the initial momentum. 5 times 8, 40 kilogram meter per second. Whereas for blue, it is 4 times 3, which is 12 kilogram meter per second. Now, if I add the two, the total answer is what? Good, 52 kilogram meter per second. That is the total momentum before they are colliding. It means that according to the law of conservation of momentum, even after they collide, the momentum, the total momentum should remain the same. Now, let us test it and see what happens when they collide. What will be their velocities and what will be their total momentum. Now they come, they collide. Good. Now we see here, after they have collided, red is now moving with a velocity of 3.556, what we are calling the final velocity. Whereas blue is moving with a velocity of 8.556. So now if we multiply 3.556 with the mass of that red box, which is a 5, we should be able to get the final momentum, which is 17.778. And if we multiply, I wanted to have that figure shown. If we multiply the velocity for blue, which is 8.556, with its mass 4, we should now get a total momentum of 34.222. Now you realize if we add 34.222 plus 17.778, we come back to our answer, which is 52 kilogram meter per second. So we are seeing that before they collided, their total momentum for red plus momentum for blue was 52. Even after they collide, momentum for red plus momentum for blue, it is still giving us what? 52. So that proves to us that the total momentum or the law of conservation of momentum is observed, or it is always maintained. We can test. I know some people may say, let us test when they are moving in opposite direction. Okay, let us test when they are moving in opposite direction. Let's say our body now, blue body, is carrying a velocity of 8. It is moving now in the other direction, and red is also moving in the other direction with that velocity. So we know the momentum is now 5 times 8, 40 for red, whereas for blue it is 4 times negative 8, which is negative 32. Meaning the momentum, total momentum before they collide is what? 40 plus negative 32. Correct, you'll get a positive 8. It means even after they collide, their momentum, total momentum, should remain positive 8. Let's run and see. They are coming together, they collide and separate. Red is now moving with a velocity of negative 6.22, whereas blue is moving with a velocity of 9.77 positive. And we see if we multiply negative 6 with a positive, with a 5 kilogram, we see the total momentum becomes negative 31.11. Whereas for the blue, if we multiply positive 9.77 with a 4, we see our momentum becoming 39.111. Still, if we add the total momentums after they have collided, momentum for red plus momentum for blue, which is negative 31.11 plus positive 39.11, you see, you still will get our final answer as positive 8. Remember, before they collided, it was a positive 8. After collision, it is still a positive 8. So this proves to us that the law of momentum is always conserved. Now that we have understood what elastic and inelastic collisions are and how we can deal with the principle of conservation of momentum, let's look at this example. A boda of mass 10 kilogram moving at 20 meters per second hits another boda of mass 5 kilogram moving in the same direction at 10 meters per second. After the collision, the second boda moves separately forward with a velocity of 30 meters per second. That we calculate the velocity of the first boda after the collision. So, from our principle of conservation, we know momentum before will be equal to momentum after. And that gives us our equation. Momentum of boda 1 before they collide plus momentum of boda 2 before they collide should be equal to momentum of boda 1 after they collide plus momentum of boda 2 after they collide. So we know the mass of boda 1 is 10, the mass of boda 2 is 5. The speed of boda 1 was 20 before they collided, the speed of boda 2 was 10 before they collided. So we can substitute them in. 10 m1 is 10. 10 times 20 plus 5 times 10 will be equal to 10 times v1, which is now the velocity of our border 1 after they collide, which we don't know, plus this for border 2, which is now 30 meters and 5 kilograms. We can now solve it, and I guess finally we can achieve our velocity for border 1 as 10 meters per second. So we realize using the principle of momentum and collisions, we can be able to solve these kind of challenges. Let's look at another scenario. This one, you can pause the video and you attempt it on your own. Then you will come back and again check the working that I showed here. So from this question, a car of mass 1,000 kilogram traveling at a speed of 20 meters per second in the direction due east collides head-on with another car Y of mass 1,500 traveling 15 meters in the direction due west. If the two cars stick together, we find their common velocity after collision. So similarly, momentum before should be equal to momentum after, substituting the values. But we know if they stick together after they collide, meaning their speed will be the same after collision. So v1 will be equal to v2. I can't decide to call it just v. After they collide, the speed is just v. So we can substitute it now in the equation. Mass for car 1 is 1,000. Velocity is 20, since it is moving in the direction of east, which is positive. Mass for car 2 is 1,500. The velocity is negative 15. Remember, it is going in the west, so it is negative. Will be equal to mass of car 1 1,000 times the velocity, which we don't know. Mass of car 2 15 times the velocity, since they have now the same velocity, vv. So we go on solving. This gives us 20,000. This gives us 22,500. This 1,000 v plus 15 v gives us that. And when we solve, we get our final velocity as negative 1 meter per second. Negative means what? It means the velocity, their final velocity is they are going in the west direction, meaning car Y ends up pushing car X because car Y was carrying more momentum than car X. That is it as far as momentum is concerned. Allow me take you to Newton's laws. This one is just a simple part, but very important and crucial. Now, what are the Newton's laws? These are just the 3 laws that summarize the behavior of particles in motion. When particles are moving, they always, the way they move, they respect these laws, or they follow these laws. And they were generated by the big man known as Sir Isaac Newton. That is the great scientist. So he's the one who realized, after serious study, he realized all bodies that do have motion, they always follow these rules or these laws. And we can start by looking at the first law, or it is known as the law of inertia. It states that a body continues in its state of rest or uniform motion in a straight line unless acted upon by an external force. Now, to put it, maybe to help you understand it, have you ever placed a stone on a piece of paper, or a ball on paper? Or you can put it, a ball on top of a table, or anything on top of a paper. Let's say a set, a calculator, a book, put it on top of a paper. When you try pulling that paper, the book will try to remain in where it was, meaning that is due to inertia. It is due to inertia. So, or if you've ever sat in a car or a bicycle, a motorcycle, and someone is driving or riding, when they try to stop the car, for you, your body tends to continue moving. So that is because of inertia. Now, this is what the law actually suggests, that anything that is in motion, it will always follow this law. If it was moving, when you try to stop it, it will always tend to continue moving. Or if it was not moving, when you try to move it, it will tend to remain where it was. That's what we mean by state of rest. So, and inertia in simple terms is just the reluctance of the body to move. A body trying not to move when it has been at rest, or refusing to stop when it was moving. That is basically what inertia is. Let's look at the second law of motion, and this is known as the law of momentum. What it says is that it states that the rate of change of momentum or in momentum is directly proportional to the force acting on the body. What do we mean here? We've already talked about momentum, and we've talked about how the momentum changes. That if a body is carrying a lot of momentum, for you to stop it, you need also to apply a lot of force. If a body is carrying a lot of momentum, it is at rest, it is of higher mass. For you to allow it to start moving, you need to apply a lot of force for that body to start moving. That is the proportionality we are talking about. And this generates for us an equation. Since we are saying it is that the rate of change of momentum, meaning momentum is directly proportional to force, meaning force is directly proportional to rate. Remember, rate we said time. So change in momentum. So the rate of change of momentum is directly proportional to force. We know change in momentum is final momentum minus initial momentum. And I can now, since I have mass common in all of them, it is one body with the same mass, I can put it outside. I can factorize it from our mathematics, and I remain here with V, and I remain here with only U when I put M out. But you realize when I have V minus U over T, it brings me a definition of something which body is defined as the rate of change of velocity, because V minus U, this is change of velocity or change in velocity. You're correct, acceleration. So we realize that V minus U over T gives us acceleration, and that's how force can be summarized as mass times the acceleration, and its SI unit, we may already be knowing it, that is a Newton. Let's look at the third law of motion, which is the law of action and reaction. This one is the favorite law, and nature does this, that for every action there is always an equal but opposite reaction. This one you can understand it when you sit for so long on a desk, it will start burning you. You start feeling hot. You stand so much on the ground, you'll get tired, your feet start hurting. Why? Because you are exerting a force on that table, on that ground. What it does, it also does the opposite. It acts on you the same way. So that is the law of action and reaction. In simpler terms, we can say when a body A exerts a force on body B also exerts an equal force, but in the opposite direction. So that is all about the Newton's laws of motion and how they help explain more the scenarios in real life. That it is to do with particles that are in motion. I will end here for today, but allow me leave you this group discussion. You can discuss it in your group, try to work it out and get the answers. The question is simple and direct. A highway bus of mass 10,000 kilograms collided with a stationary roller of mass 15,000 that was undergoing repair. After collision, the bus got stuck and moved with a lorry at a speed of 10 meters per second. According to the footage captured on phone, the eyewitnesses claim the bus was overspeeding. That's why it lost control when the driver saw the lorry on road. The signpost around that area indicates a speed limit of 20 meters per second. Now, help the traffic police to confirm whether the eyewitnesses are telling the truth. So in your groups, discuss this, show your necessary working, so that you can come to a conclusion that will help this traffic police to know whether the witnesses are saying the truth that the bus was overspeeding or not. That's all I have for you today. Allow me wish you a blessed day till we meet in another lesson. Have a good day. Bye bye.